Hi everyone, I'm Vincent Leung from Imperial College London. Thank you for having me in ICASSP 2020. And today I'm going to present my paper, Reconstruction of FRI Signal using Deep Neural Network Approaches, co-authored by Junjie Huang and Professor Pierluigi Dragotti. We start with introducing a simple acquisition device where we have the input continuous time signal X. To process it, we typically filter the input signal with a sampling filter H before sampling at a uniform interval T. In this paper, we focus on the reconstruction of the continuous time signal from its corresponding samples Y. Classical sampling theory has shown that perfect reconstruction is possible when the input continuous signal is band-limited and when the sampling frequency is twice the bandwidth of the input signal, and also when the sampling kernel phi is a sinc function. However, this is rarely the case for signals in real life, as we would often deal with time-limited signals, and time-limited signal cannot be band-limited at the same time. This led to the development of finite rate of innovation sampling theory, which extends the classical sampling theory to classes of non-band-limited signals with finite number of degrees of freedom per unit time. Perfect reconstruction is possible with sampling kernels with certain properties, which we will introduce later on. Here, we give an example of a signal with finite rate of innovation, a stream of k Diracs. The rate of innovation of this signal is Tk, which refers to the amplitude and the location of the Dirac deltas. We are particularly interested in this basic FRI signal because many phenomena can be modeled as a pulse shape convolved with a stream of Diracs, allowing us to extend the reconstruction framework onto a wide range of applications. So, how do we reconstruct a stream of Diracs? It requires the sampling kernel to satisfy the generalized Schramm-Fix conditions, such that the weighted sum of the kernel and its shifted versions will reproduce exponential polynomials. Two very common types of sampling kernels are polynomial reproducing functions, like B-splines, and exponential reproducing functions, like E-splines. Let's now take E-spline as an example and see how classical FRI reconstruction method works. We begin with the samples Yn. When the input signal is a stream of k Diracs, as the acquisition device can be viewed as a simple convolution, we can rewrite the samples into an amplitude-weighted sum of the sampling kernel phi. Using the coefficients of an exponential reproducing function, we can then map the samples into a sum of exponentials, which forms a spectral estimation problem. Note that the sum of exponential is linear with respect to the amplitude ak, yet nonlinear towards the location tk. This has motivated us to focus on solving the locations of Diracs. A spectral estimation problem is classically solved by SVD-based subspace estimation methods. For example, the Prony's method and matrix pencil methods. When the samples is corrupted by additive white Gaussian noise, the performance follows the Cramér-Rao bound at high peak signal to noise ratio, yet breaks down when the PSNR drops below a certain level. We call this the breakdown PSNR. In order to improve the breakdown PSNR, firstly, we investigate the reasons behind this breakdown. The breakdown in performance is conjectured to be caused by the subspace swap event that happens when the signal subspace is estimated incorrectly due to the corruption of noise. As the breakdown PSNR is the point where the necessary condition of the subspace swap event is fulfilled. Here gives an example of recovering the locations of a stream of two Diracs with equal amplitudes. The vertical axis refers to the breakdown PSNR, and the horizontal axis refers to the distance between the locations of neighboring Diracs. It means that when the Diracs are sufficiently far apart, this breakdown PSNR remains at a similar level. On the other hand, when the Diracs are really close together, the subspace swap event is more likely to occur and hence breakdown PSNR increases. As the subspace swap event is inherent in classical subspace methods, this leads us to think if there are any other ways to approach the FRI reconstruction problem. Ideally, we would like to reduce the breakdown PSNR for cases where the Diracs are really close to each other. Meanwhile, at least performing as well as the classical methods when they are far apart. A visualization using the figure is simply that we would like to push the breakdown PSNR towards the left. Therefore, in this paper, we have proposed two deep neural network-based approaches. This is because DNN-based methods have achieved state-of-the-art performances on many signal processing problems by learning from a large amount of training data pairs. We hope to exploit the advantage of DNN and existing training data to improve the reconstruction performance. The first approach is direct inference of FRI parameters. The idea is to have a deep neural network with its input being the noisy samples to the y, and its output being the estimated locations t hat. This idea is motivated by the fact that it does not involve the subspace estimation like the classical methods. We hope that by parsing the SVD-based methods, we may reduce the occurrence of the inherent subspace swap event. Another interesting point is that this method does not require any explicit information about the sampling kernel. By feeding the network with a large amount of training data filtered by the same sampling filter, the network will learn the relationship implicitly. For the network structure, it consists of 3 convolutional layers, followed by 3 fully connected layers of size 100, 100, and k. Each of the convolutional layers has 100 filters of size 3. ReLU is used as the activation function between each 2 layers. The loss function we use is the mean square differences between the estimated locations and the true locations of the Diracs. Backpropagation with Atom Optimizer is used for learning. The second approach is to use deep neural network as a denoiser on the noisy samples, followed by a subspace-based methods to estimate the FRI parameters. This approach is motivated by the possibility of lowering the breakdown PSNR without significantly altering the performance in the no-noise regime, as the subspace-based methods are still used to perform FRI reconstruction. However, as subspace swap events are inherent in those methods, they may still remain in this approach. The training setting is similar to that used in direct inference approach. The only modification in the network structure is the change in the size of the 3 fully connected layers to 100n, 20n, and n respectively. The training loss function is the square difference between the denoised samples y hat and the noiseless sample y. Moving on to the simulation setup. The simulation focuses on the basic setting of reconstructing a stream of 2 Diracs with locations between negative 0.5 and 0.5 and a positive amplitude. The number of samples and sampling period are set to 21 and 1/21. We then train a network for every PSNR from negative 5 to 70 dB with a step of 5 dB. Each of the network is trained with 100K of training data, with its location uniformly distributed across the whole timescale, and the amplitude uniformly distributed between 0.5 and 10 to cover a sufficiently large part of the positive amplitude subspace. For the sampling kernel, to test the theoretical bound, we opt for the optimal settings for subspace methods, which is an EMOMS. This kernel can reproduce an exponentials that are evenly spaced around the unit circles. This allows us to see where the limit is for the subspace method and whether the neural network-based methods can overcome it. To evaluate both methods, we use the standard deviation of the estimated location with respect to the actual location. We fix the first Dirac at t equals 0 and change the location of the second Dirac from 10 to the power negative 0.5 to 10 to the power negative 3, evenly on a log scale with a step of 1/4. To allow us to compare with the breakdown PSNL bound shown before, we set the amplitudes of the Diracs to both be 2. By performing the Monte Carlo simulations with 10,000 test data for each distance, we obtain the following results. Here shows the results of our proposed method compared to the classical matrix pencil method. The red dotted line refers to the breakdown PSNR using subspace-based methods. That is the necessary condition for the subspace warp event to occur. Yellow indicates the high standard deviation, while blue indicates a low standard deviation. In other words, the bluer the region is, the higher the reconstruction performance it achieves. Firstly, as expected, the matrix pencil method performs very well when the PSNL is high and the Diracs are sufficiently far apart. However, once it reaches the red dotted line, the performance deteriorates. On the other hand, we can see that both neural network approaches lowers the breakdown PSNR, indicated by the spread of the low standard deviation region across the red dotted line. Comparing the two network-based methods, the deep neural network denoiser fails to push the breakdown PSNR boundary. This could be explained by the no noise power in the samples, which leads to the minimal difference between the noisy samples and the ground truth samples. So, even though it has outperformed the direct inference approach when the PSNR is high and the Diracs are sufficiently far apart, the top right region, the denoiser has a limited impact to the breakdown PSNR. As our goal is to enhance the performance in the breakdown regions of the traditional subspace-based methods, we focus on the distinction between the matrix pencil method and the direct inference method we propose. Let's take a closer look by investigating the two individual cases with different distances between neighboring Diracs. We start with a case where the Diracs are relatively close to each other. Here shows the scatter diagram of the estimated locations using the two methods over 100 realizations for each PSNR. As we can see from the diagram, the direct inference method has reduced the breakdown PSNR from 40 dB to around 20 dB. An alternative case is when the Diracs are sufficiently far apart. We can see that the breakdown PSNR of the matrix pencil is now lower, while our proposed method has a similar breakdown compared to the previous slide. Moreover, we can observe that the centers of the scatters at high PSNR are not entirely aligned with the true locations. A possible reason could be the generalization error of the neural network in performing the reconstruction tasks with a high precision. This result suggests that direct inference approach is successful in lowering the breakdown PSNR regardless of the locations of Diracs. Nonetheless, it has a room for improvement when the signal of interest is far from the breakdown PSNR. To conclude, in this paper, we have proposed two ideas on reconstructing signals with finite rate of innovation based on neural networks, including the direct inference method and denoising method. Both methods can reconstruct FRI signals at the low PSNR region where the existing methods would break down. However, this comes with a performance compromise in high PSNR region. Hence, in the future, we'd like to remove this compromise by exploring ideas that incorporate the advantages of the classical FRI methods, such as providing the network with explicit information about the sampling kernel and design network architecture that include the classical methods in an end-to-end training. That's the end of the presentation. Thank you for your attention and feel free to ask me any question.